Hi everyone, in this video I'm going to go through an infinitely repeated prisoner's dilemma where our players are playing a grim trigger strategy. And in this video I'm going to solve for delta, that's our discount factor, and R, the interest rate that allows for cooperation. So that's a common sort of question that you'll get with these sort of situations. You can check the description for timestamps if you want to skip ahead to any part of the video, and I have done previous videos on the prisoner's dilemma if you find you need more background to this topic. I'll link to those videos above and in the description. Just to give you a very quick rundown though, so this would be an example of a prisoner's dilemma. We have two players that, in my example, they're choosing between playing high or playing low. Up here is what we call the cooperative outcome. In my example, that's where both players play high and both players get an outcome of 10. And it would be pretty good for our players to be here. It's not the best place for them individually. Both of them would rather get to those 17 outcomes. That's, I think, the highest payoff that they can get. But the cooperative outcome is Pareto efficient. If we're here, we can't move to any other outcome without making at least one person worse off. Down here, where both of our players play low, that's the Nash equilibrium of the single shot version of this game. Our players get a fairly low outcome of 5 each. It's Pareto inefficient. Both players would be much better off at the cooperative outcome where they get 10 each. But low is the solution of the single shot simultaneous version of this game. And the reason really why the cooperative outcome is not a solution to the single shot game, why it doesn't end up being a Nash equilibrium, is really because of these payoffs here, the 17s. If player 2 plays high, player 1's best response is to play low and get 17. If player 1 plays high, player 2's best response is to play low and get 17. So both of our players playing high is really not going to happen in the single shot version of this game. And really the take home of this game is that the prisoner's dilemma raises this issue of how can we get our players to cooperate with one another? How can we get them both to play high? It's a real dilemma. And actually, the idea of repeated games is a potential way out of this dilemma. So how does it work? Well, if we allow for repeated interactions, we are going to let our players play this game over and over again. We call the matrix a stage game, and each time our players play, we call that a stage. If it's an infinite repetition, which is what we're talking about here, this repetition goes on forever. And the key thing about repeated games is that it actually allows our players to react to what happens in a previous stage. So actually, when we think about a player's strategy, a strategy is like a plan of action for the game. If we think about a single shot, a simultaneous game, the strategies are usually really simple and often just equal to the possible actions. So, up or down or high or low. When we have repeated games, a player's strategy will be more complex. The strategy will define all of the actions that a player will take at each stage for all possible histories that a player might face. And a history is just a description of what happened in all the previous stages in the game up to the point that we're considering. In this video, I'm going to be thinking about a grim trigger strategy. And a grim trigger strategy is one where our players will choose the cooperative action as long as everyone has cooperated in all previous stages. So if I write it out, it would be play high in the first stage, so that's cooperate. Then play high as long as in all preceding stages, the outcome was high. So they both cooperated, both players cooperated. Otherwise, play low. So that's our grim trigger strategy. It describes what our player is going to do at each stage, given every possible history. And I suppose the name trigger is telling. Under this strategy, any non-cooperation will trigger a move away from cooperation back to low forever. It's a very unforgiving strategy. It's very harsh. If anything is going to work, it's going to be grim trigger. And actually, grim trigger can lead to continued cooperation between our players. It can solve this problem of the prisoner's dilemma, but only under certain circumstances. To see this, let's imagine that we're player 1, and let's assume that player 2 is playing grim trigger. What is player 1's best response to player 2 playing this strategy, this grim trigger strategy? Well, we have to compare the payoffs of each of player 1's possible strategies, which is either they can play grim trigger as well, or they can defect and they can not cooperate, they just play low. And when we think about payoffs associated with the different strategies, when we have these repeated games, our payoff associated with each strategy will be the present value of the sum of the series of payoffs that our player will get going on into the future at each stage. So let me explain, and I'll bring up a table where I'm going to detail player one's payoffs at each stage of our game. So stage 1, stage 2, stage 3, etc. And then ... That's the payoffs that player one will get at each stage forevermore. So off onto infinity, because we're playing an infinite amount of times. And this is going to be given that player 2 plays Grim Trigger. And I'm going to think about the payoffs at each stage when player 1 also plays Grim Trigger. Now we can also note here that as we repeat the game, the passage of time is passing. So we can think about each one of these stages as occurring at different times. So the first play will be at time t is equal to 0. That will be like the present time, so today. T is equal to 1, that's the next period. T is equal to 2, that's the time period after, etc. Then ... that's forevermore. And well, if player 2 is playing Grim Trigger, then in the first stage, that first period, they will play the cooperative action, they will play high. If player 1 plays Grim Trigger as well, then they will also play high in that first period, so they both play high and player 1 gets 10. Now, given that they are both playing Grim Trigger, in the next period, they will both play high again, since no one has played low in any previous periods, so player 1 gets 10 again. In time period 2, both will play high again because no one has played low in any of the previous stages, so they both get 10 again. And actually player 1 gets 10, and it will be like this forever. They will get 10 forevermore. If both of our players play Grim Trigger, then no one plays low ever, because no one ever plays low. And you can actually see that both of our players playing Grim Trigger is really synonymous with cooperation. All right, let's put up another table. And well, player 1 could alternatively defect from the Grim Trigger. They could not cooperate, they could play low. And this means that they will get an immediate payoff, that higher payoff of 17. Because remember, player 2 is playing Grim Trigger, so they are going to cooperate in the first stage. After that though, because it is Grim Trigger, that action triggers no more cooperation from player 2 or player 1. So both players play low, so player 1 will get 5 at t is equal to 1, t is equal to 2, etc. 5 forever. Now the question of whether player 1 should cooperate, so if they should play Grim Trigger or not, if they should play low, given that player 2 is playing Grim Trigger, really comes down to whether the payoffs, so the present value of the sum of payoffs over time associated with Grim Trigger, whether that is greater than or equal to the present value of the sum of payoffs associated with defecting. Now, I've been talking about present value, and just to explain, the idea, as we've seen, our players' payoffs are being paid over time, but because of what we call the time value of money, we need to bring back future payoffs back to their present value. It's called the discounting. And only then, when we get the present value of all of our future payoffs, can we get a meaningful number when we compare our strategies. And we get the present value by discounting future payoffs by our discount factor. I'm going to use delta, and we're going to discount each future payoff by multiplying those future payoffs by delta to the power of t, where t is the time period when the payoff will be received. So I have done a video on the time value of money and discounting if you need more background. So I'll link to that video in the description and also in the corner up here. But this is the formula we need to discount our future payoffs. So back to our tables then, and thinking about player 1 playing Grim Trigger if player 2 plays Grim Trigger, so cooperation. And our formula for discounting is up here. We're multiplying each future payoff by delta to the power of t. Well, then I'm going to construct a sum, S subscript G, that will be the sum with Grim Trigger, will be equal to, well, in that first stage, we get 10, and that will be times delta to the power of 0, where t is equal to 0. And then we add to that, we get 10 when t is equal to 1, so it will be 10 times delta to the power of 1, plus 10 times delta to the power of 2, that's when t is equal to 2, plus 10 times delta to the power of 3, etc., ... we get that forever. On the other hand, the sum associated with defecting is going to be equal to, well, I'll just call it SD, the sum for defecting. Well, we get 17 in that present period, so that would be 17 times delta to the power of 0. And then we get 5 forevermore, so 5 times delta to the power of 1, plus 5 times delta to the power of 2, plus 5 times delta to the power of 3, etc., etc., ... forevermore. And so it's really these two sums that are important. These are our payoffs. And we can find these sums as long as delta is between 0 and 1 non-inclusive. And this is because actually here and here, we call these infinite geometric series. The string of payments of 10 discounted in the future, and this part here, the string of payments of 5 at every period, all the way to infinity, they're infinite geometric series. And we actually have this formula here, the sum of an infinite geometric series, I'll call it big S subscript infinity, is equal to A divided by 1 minus delta, where A will be the constant amount that we get in every period. So I have done a video showing how we get to this formula as well. I'll link to it in the description and above. And this formula is correct if our infinite series starts at t is equal to 0. And of course, as I said before, as long as delta lies between 0 and 1. And just to give you an intuition around this, as t gets bigger and bigger, as long as delta lies between 0 and 1, delta to the power of t will get smaller and smaller and smaller. And this means that the present value of our payoffs gets smaller and smaller and smaller as we get further and further into the future. And when we take t as approaching infinity, the present value of the payoffs really far off into the future, they're basically 0. So the sum converges to a finite amount. So we can use our formula actually quite easily in the case where our players both cooperate when they both play Grim, because our A is just equal to 10. So the sum of the infinite series is 10 divided by 1 minus delta. Now the present value associated with defecting is equal to, well, we said before we get this initial payoff of 17 times delta to the power of 0 plus kind of 5 forevermore discounted. So we have a different first number and then the infinite geometric series, which starts at t is equal to 1, not t is equal to 0. But it's no big deal. So we start with the 17. Now anything to the power of 0 is equal to 1. So we just get 17 because delta to the power of 0 is just equal to 1. And then we get plus. We're going to apply the formula. The constant payoff is 5. So I get 5 divided by 1 minus delta, but I'm going to multiply this whole term one more time by our discount factor. We're going to discount it one more time just to account for the fact that our infinite geometric series is starting at t is equal to 1 and not t is equal to 0. So that will fix our problem and allow us to use this formula in this slightly different context. So this is player 1's payoffs associated with playing Grim Trigger, given that player 2 is playing Grim Trigger, and this is the payoffs associated with defection, given that player 2 is playing Grim Trigger. And Grim Trigger will be a best response for player 1 to player 2's playing Grim Trigger only if the payoffs associated with playing Grim Trigger is greater than or equal to the payoffs associated with defecting. So if SG is greater than or equal to SD. And just substituting our payoffs then, this reduces to if 10 divided by 1 minus delta is greater than or equal to 17 plus 5 times delta divided by 1 minus delta. Let's solve for delta. We can multiply both sides by 1 minus delta, and that cancels out on the left-hand side. And on the right-hand side, we get 17 times 1 minus delta, plus that cancels out as well. So we get 10 is greater than or equal to 17 times 1 minus delta plus 5 times delta. Let's open these brackets out and we get 10 is greater than or equal to 17 minus 17 times delta plus 5 times delta. If we take away 17 from both sides and we add 5 times delta to the negative 17 times delta, we get negative 7 is greater than or equal to negative 12 times delta. We can then divide both sides by negative 12 and we get the condition that Grim Trigger will be a best response for player 1 to player 2's playing group trigger if delta is greater than or equal to 7/12. When we divide it by the negative, I switch the direction of the inequality. Now, if you remember back to our matrix, we have a symmetric game. So player 2's payoffs are exactly like player 1's payoffs in exactly the same sort of situation. So everything's kind of symmetric. And so this means that delta greater than or equal to 7/12 will also be player 2's best response if player 1 plays Grim Trigger. And so then we get the outcome that the two players playing Grim Trigger to one another will be a Nash equilibrium, an intersection of best responses, if delta is greater than or equal to 7/12. And if that happens, then we get cooperation. We get both of our players playing high indefinitely. And so that's a result. I've only really got a little bit more to go. Let's try to understand this result a little bit. And the first thing to note is that delta needs to be greater than or equal to 7/12. So delta needs to be higher than some limit. And sometimes you might see textbooks say things like, cooperation will be possible if delta is close enough to 1. And remember, delta needs to be between 0 and 1. So when we're saying that, we're saying that delta needs to be quite high. Let's think about that. A larger or higher delta means that our player is not discounting future payoffs heavily. So basically, our player is pretty patient. They're willing to wait for their payoffs. They don't matter so much if they happen in the future. A high payoff in the future means almost the same to them as a high payment today or now. And that means, in the context of the prisoner's dilemma, that the series of medium-high payments that cooperation will give our players when they cooperate, in our case that's 10 in each period, even though those payments are happening in the future, it still means a lot to our players, and they won't forgo those payoffs in favor of that one very high payoff of 17 that they get straight away if they defect. So as long as our players are patient enough, then cooperation is possible. Now, what determines this patience? Well, in the sort of interpretation I just discussed, delta can include personal preferences for whether we get a payoff sooner or later. But a very common easy case, though, is to not include all that stuff in delta, but instead only include a measure of the fact that money that we get now, we can invest in the bank and we can earn interest on. And so what matters in this kind of simple case is just the interest rate. And so delta is very often just equal to 1 divided by 1 plus r, where r is the interest rate. Again, you can see my time value of money video for more information on how we get to this condition. But when we have something like this, we can solve for the interest rate that allows for cooperation. So substituting in 1 divided by 1 plus r for delta, we get the condition that 1 divided by 1 plus r needs to be greater than or equal to 7/12. So we can solve for r, we can multiply both sides by 1 plus r, and we get some stuff cancelling out, but we can also multiply both sides by 12. So we get 12 is greater than or equal to 7 times 1 plus r. We open up that bracket, and that reduces to 12 greater than or equal to 7 plus 7r. Take away 7 from both sides. So we have 5 is greater than or equal to 7r. Divide both sides by 7, and we get this condition that we need the interest rate to be less than or equal to 5/7. And this again makes sense. If the interest rate is high, the money that we receive now, the payoffs that we receive now, we can invest in and earn higher interest from. And as a result of this, we discount payoffs received later more. They matter less to us relative to monies received sooner. So the relatively higher payoffs of 10 that player 1 and player 2 will get in the future from continued cooperation, it matters less to them than especially that initial payoff of 17 that our players would get if they defected from the strategy. The 17 is really attractive when the interest rate is high because that's more payoffs, more money that they can put in the bank and earn interest on. When the interest rate is low, however, we don't get these pressures to get our payoffs, our money sooner, so we can put them in the bank. So hopefully that makes sense about the interpretation of delta. and when we introduce the interest rate, why lower interest rates will be better for cooperation and higher interest rates worse. Now, I should say you can get more complicated discussions around this if you want to show subgame perfect equilibrium, for instance. There are some other results that you see discussed occasionally, but I don't want to overwhelm you, and so many textbooks that I have really don't go further than what I've presented to you here. So I'm just going to leave the video here. Just let me know in the comments if there's anything else you want me to cover. All right, that's it for me. I hope that this helps. If it did, please like and subscribe. You can also check out my website, www.econhelp.com.au. You can access additional stuff. There's not much up there at the moment, but over time there'll be more stuff. So that's it for me. Thank you so much for watching this video. I hope it helped. Have a great day.